Mhm. Okay. Today we finished the topic of working memory. Why is working memory interesting? Why should we care about it? Well, clearly we care about it if we want to memorize things. But why is it interesting as a dynamical phenomenon? Of? So the issue is that when we look at working memory, both at behavior and the neural correlate or the putative neural correlate, it seems that the time scale of the neuron and the synapses is a few orders of magnitude shorter than the time scale of the actual dynamics in the brain, and therefore it's an interesting dynamical puzzle. Even if we don't care about the brain, if we just care about dynamical system, then it's an interesting puzzle. And different models have been proposed, or different mechanisms have been proposed over the years, and we can differentiate between them on a biological basis. For example, we can ask whether working memory or the mechanisms underlying working memory are single cell mechanisms or network mechanisms. I showed you one example, one experimental result in which single neurons that demonstrate that single neurons in the entorhinal cortex are endowed with a capacity of doing something like integration and long-term memory. Since then, there have been attempts, which is like 10 years ago, to see whether similar phenomena exist in more biologically plausible conditions, and there was some success, but still most of the community believes that in most cases working memory is the outcome of a network interaction. And then we discussed three mechanisms for working memory. So one way of differentiating models is single cell versus network, but another one is to talk about differentiating between mechanisms based on the dynamical properties or on the mathematical properties of the solution. So what were the three mechanisms that we discussed? Before that, what was the first one? When we talked about the recurrent network. So the idea was, the first mechanism that we discussed at length was an attractor-based mechanism. The idea was that the attractor is endowed with what's called line attractor, or manifold attractor, and the idea is that there are directions, thinking about it in the framework of an energy landscape, there are directions in which there is a fast convergence to the fixed point, and there are directions where the fixed points are marginally stable, and memory is stored in the steady state location, in the steady state of the network, using this idea of line attractor. So this was the first mechanism. There was another mechanism that we only briefly discussed, and this was feedback or method that a mechanism that required the computation of the derivative, and then with feedback we showed that the time scale of the effective time scale of the dynamics can be arbitrarily long if this feedback control is sufficiently strong. And the third mechanism, this is the mechanism that you started discussing, was a mechanism in which we posited that the memory is not in the steady state, but in the transient of the dynamics. And one example that we discussed was the delay line. And we discussed a discrete time delay line because it's easiest to understand. And then we came up with a continuous time delay line. And I will just write down the equations. So the equations were, let's do it here. Tau r dot is equal to minus r plus jr. And the structure of the connectivity was something like this. So I'm using J both to denote the scalar, the strength of the connectivity from one neuron to the other, but also to denote this matrix that of diagonal terms are equal to J. One below the diagonal terms equal to J. And then we did we assumed that there is a delta increase in the activity of the first neuron, and we considered the activity of a readout neuron that reads the activity of all neurons. And just change to something more comfortable. Okay, so we did the math, and we concluded by saying that the activity of the output neuron is equal to e to the minus t over tau times sum over j of t over tau to the power of j over j factorial, and this goes from 0 to n minus 1. So this was the conclusion, and from this it's easy to see that the limit when n goes to infinity of our output is just equal to 1. So the memory of the pulse input to the first neuron is never lost. Now clearly this is true only in the limit of an infinitely large network. For example, if there's only one neuron in the network, if n is equal to 1, then it's very clear that the dynamics will decay to 0 within tau. And I ask, the question that I asked you is, how large should n be? So we have some insight from the discrete network, from the discrete time network. And there we saw that memory is maintained. Well, what did we see there? How did the time scale of the network, or the memory of the network, depend on the number of neurons? On the delay line, discrete time delay line. question is the following. In the discrete time network, how long does the network remember the input? And how does it depend on the number of neurons?
The more neurons, the longer the time.
Can you be more quantitative, more accurate? And delta t. So we assumed in the discrete time network that there is information or the activity propagates in steps where the time it takes information to propagate from one neuron to the other is delta t. And if we have n neurons in the network, then it can remember the input for n times delta t times, well, n times steps, or n delta t. So what's the expectation from this continuous time network? What do we expect based on our intuition from the discrete time network? So what's delta t in the continuous time? What's the correlate of delta t? Tau. Because this is the characteristic time of the neuron, this is the time it takes the neuron to respond to its input. So we expect that this network will be able to integrate or memorize inputs for n times tau time units. How can we prove it or test it? Well, let's look at this sum. Okay, we have a sum of n terms here, and well, we can write it as this would be equal to e to the minus t over tau times e to the t over tau minus sum of j going from n to infinity to t over tau to the power of j divided by j factorial. Right? I'm taking the complement of this sum, and then I get the e to the t over tau. But I need to subtract this tail or the residual of this infinite sum. So this would be equal to 1 minus e to the minus t over tau times sum over j from n to infinity of t over tau to the power of j over j factorial. So if this sum is small, then this term would be negligible, and then we will stay with 1. If this sum is large, then we have a problem. So we can ask for what values of t can we be sure that this sum is small? Or we can ask for what values of t each element here in the sum will be small. So let's look at at the first. Let's look at the first element in this sum. So what's the first element in this sum? The first element in this sum is t over tau to the power of n over n factorial. And we want this term to be very small. The question is, what would be the value of t? What would be the values of t such that this inequality is satisfied? Well, smaller than tau is a correct answer, but not a very useful one. Smaller than tau, this would, I mean, if t is substantially smaller than tau, then the single neuron will effectively be an integrator. So how are we going to solve this inequality? Okay, how are we going to use the Stirling approximation? Well, first I will take a log. So I'm going to take a log, and then n log t over tau minus log of n factorial should be much smaller than 1. And then we can use the Stirling approximation. So the Stirling approximation tells us that for large n, the logarithm of n factorial is equal to n log n minus n. This is called the Stirling approximation. I don't know how Stirling. Itamar, is it the right? I don't think it's with an I. I think it's with an E. It's easy. Well, you can just Google it and find out. Then I will, if I'm wrong, then I will argue fiercely that it was an I. So the requirement would be that n log t over tau should be much smaller than n log n minus 1. Or t over tau should be much smaller than n over e.
Okay, but the Stirling approximation is only for the limit when n goes to infinity.
Yeah.
And we're assuming this case.
Well, we're interested in well, if the network is finite then or small, then you can just take the sum. Let's return to the sum and first linear. But typically we're interested in large networks. And if you want to ask how large should it be for this approximation to work, then we need to work out the correction of this approximation. But in the limit of a large n, this will work as a good integrator as long as t is much smaller than this tau prefactor, which determines the time scale of individual element, which the time scale of individual element times the number of neurons in the network. Questions? What about, okay, so this was for the first one. What about the second term? We have an infinite sum, so we did the first one. And now we need to go and do each and every one, right? What about the second term? Well, clearly, if this is true for n, this will also be true for n plus for n plus 1, n plus 2, and so on. And I will not prove it, but this sum is dominated by the first one. Questions? So now, okay, now we have an example of an integrator that works, that integrates in time scales that are on the order of tau times n. So we have one example. It's qualitatively different from the first example that we discussed in the working memory, again, because this is integration using the transient of the dynamics. It's not using the attractor or the steady state of the dynamics. Dynamics will converge eventually to zero in the absence of input. But convergence will be much slower than the characteristic time of the neuron. One may be interested in the question of how this can be generalized, and I'll explain what I mean by that. So, when we discussed integration or line attractor, we started with an example. I can't remember what was the example. It was R1 dot is equal to minus R1 plus JR2, and R2 dot is equal to minus R2 plus JR1. Was it plus or minus? I can't remember. Let's assume that it was plus. And then we found that when j is equal to 1, something interesting is happening that is relevant to the question of working memory. And then we generalized it and found out that in general, considering linear networks, when one of the eigenvalues of the connectivity matrix approaches 1, then the network behaves like an integrator. So this was a generalization of this example. And then we had other examples where the OTAs, this was another example, but they all shared in common the fact that one of the eigenvalues approaches 1. So the question, what is the generalization here? Or maybe I'll ask a simpler question. Can we construct other networks that will share this property, that in some way will integrate input in a similar way to this one, but using a different architecture? So this is my question to you. Can you think of other examples like this one, or generalization of this one? So are there other connectivity matrices that share this property? So I'm going to give you, to show you how other matrices can be constructed, and then Itamar will replace me, take my place, and tell you about a different problem, or we'll discuss a different computation, and eventually, hopefully, we'll provide you with a rigorous mathematical analysis of the example that I will describe. So I'm going now to introduce the family of unitary matrices. Unitary. So unitary matrices are matrices such that U transpose is equal to the inverse of a matrix. Actually, it's a complex conjugate, but we will think about real matrices.
I sometimes call them orthogonal matrices.
I'm sorry?
I call them orthogonal matrices, but you know that they're both valid.
Okay, orthogonal. So now let's consider a connectivity matrix that looks like Uj U transpose. So I'm going to take the original matrix here, this J matrix here, and I'm going to multiply by U from the left and U transpose from the right. So let's look at the dynamics. So now we have tau R dot is equal to minus I minus J R. So other than J, this should be U J U transposed R. So we are interested in understanding the dynamics in using this set of linear equations. So let's multiply this equation by U transposed from the left. So tau U transposed R dot is equal to minus U transposed R. This would be the first term. And because U transpose is equal to U to the minus 1, U transpose U is equal to I. So we are left with J U transposed R. Or we can just write it as minus I minus J U transpose R. So if we replace J by Uj U transposed, then the dynamics of U transposed R will follow the dynamics of R in this example. So any transformation of the connectivity matrix in this way will result in an effectively identical dynamics, but in a different base. Dynamics for the U transpose R. Questions about this? So this is a good place to stop. This concludes the chapter on working memory, and the next chapter would be on selectivity. And we will start with Itamar describing a simple example of amplification.
You guys prefer to have a break now and then we'll go all the way through to the end, or keep going now for 15, 20 minutes? Any preference?
Don't stop for now.
What?
Don't shower for 2 minutes.
Just keep on going. Alright, one preference is good enough. Keep going. That's democracy, if only one person votes. Jeez. Okay, you guys will get to see this example. Like Jonathan mentioned, I'll come back to this at the end of this topic, and you'll get to see it in the upcoming exercise. But with that, we're switching gears and switching topics. So, like Jonathan said, the new chapter will be selectivity. So, selectivity of the stimulus, networks that have some kind of form of selectivity. I guess it's chapter 3. And our first example of that is amplification. So generally in this whole chapter we'll be dealing with systems that have input that we can think of as some kind of sensory input representing the external world, and we want to have selectivity or sensitivity to that input. So in later parts of the chapter we'll deal with selectivity in the sense of actually being more sensitive to certain inputs versus the others. And in the first stage is just amplification without really being differentiating between different inputs. So what I mean by amplification is that I would like to construct here a system that is very responsive to changes in the external input that it's receiving. So it's going to amplify its input and also hopefully respond very quickly. So we're gonna look only at linear systems, linear networks. So we have a linear network, the same form as Jonathan already wrote up here, as we've been studying for the last while. R dot minus R plus J is connectivity mix plus R, and then we have some external input vector which can depend on time. And we'll look, for example, at an external input that's a step function. That's a kind of simplest case. So some scalar parameter, just saying how large the input is, and then a step function, which is sometimes written like this with like a capital theta, and it just looks like this, right? Step function at time 0, we have a step of size h0. And we want quick and large response in our network. Okay, so how do we see what the response of the network is going to be? How do we solve this system of equations that we've been already like grinding into the dust over the last few weeks? How do we solve it? Should be like a chorus, like like all at once the Greek chorus sings eigenvector decomposition, something like that. So we know we can transform this, assuming that the matrix is totally has n eigenvalues. We can immediately write in the eigenbasis with the components of the eigenvectors C. equals minus, and we have here -1, and I'll bring it inside the parentheses, lambda k, the eigenvalue, the case eigenvalue of the matrix J, times ck. And then we'll have some external drive, the projection of the external drive onto the on the eigenbasis, which I'll call C0k. Right? So that's good. We're so bored with that already. We've done the eigenvalue decomposition. We have decomposed dynamics in n separate dimensions. And now I want to see what's the response going to be to this kind of input. So if this goes on for very long, we can see that we have a fixed point eventually, right? Let's see what that fixed point value is. So the fixed point value eventually, if we hold on for long enough, ck star is equal to 1 over 1 minus lambda k ck0. And we can see from that the eventual steady state, if this is held long enough, so we have whatever the external input is on that eigenmode, times this factor, 1 over 1 minus lambda k, which I'll call that AK, A for amplification. This is a kind of amplification factor, whatever the external drive is on the eigenmode, the steady state of the actual dynamics on that mode is just multiplied by AK, right? So we can start to think about whether we're amplifying, whether we're not, how we can amplify best already here, right? If this factor is large, then it looks like we've done well and we have a large response. So for that, we would want right, lambda k to be smaller than 1. Right? If lambda k is larger than 1, we have a problem. The whole system diverges. But if lambda k is close to 1, then this AK can be very large. We can get a very large response. That's what it looks like. Okay, and then going back to the time-dependent solution of this equation. So just assuming for simplicity that we start at time 0 at rest, we're at 0. So then what's the form of this solution?
Why do we assume the current itself is very long?
We don't necessarily assume. This was just to kind of give us a sense of what will happen. So in the case in which it's very long, this will be the fixed point. If it's very short, then I kind of know I'm approaching that. I may not get to that point. But that's just to kind of give me a sense. But the full picture, kind of regardless of the length of the actual input, will be given by the full time-dependent solution. So assuming we started at time 0, what's the solution? This is like almost Greek chorus level, not quite, but like you should be pretty ready to just like whip this right out. What does it look like? So this is a good one to be like. Some people like to say if someone comes and wakes you up in the middle of the night. I don't know. That's like a little bit like violent. We're just talking about dynamics, so we need to get that serious about it. But you know that the full solution, there's a solution that we've seen with an integral and an integrating factor and all of that. But there's a much simpler form if we know that this is fixed in time. Like in our example, the external drive, we can think about it as totally fixed in time, and we just start at time 0. So that's kind of a solution you should really know. That essentially the dynamics are exponential, but they're kind of a flipped exponential, right? Starting at time 0, we're letting the system go, and it's starting at level 0, and it's going to have an exponential decay to the new fixed point level, which the level is determined by AK, but it's kind of got this exponential form like that. Or say this is AK CK0 here, and it's got this exponential upward decay, and it's just 1 minus e to the minus t. Now, what's the time scale? So, in order to find that solution, again, I would divide by 1 minus lambda over k over here, so I get the exponential would be t divided by tau over 1 minus k, lambda k. And all that is multiplied by the eventual fixed point value, if we were to reach it, AK CK0.
What's the answer 1K?
what's written here? Tau over 1 minus lambda k. I'll write that again here. So that whole thing, that's like an effective time scale. So I'll call that over here tau k. So tau k, the effective time scale of the case mode is tau over 1 minus lambda k. Okay. And if that solution is not obvious to you of how we get to here from here, then you should make sure to go do it at home. You can start by solving it without an external input, and then think about the constant external input as just as a shift. I think I did it in the bonus hour as just doing a change of variables to shift according to this factor here. Okay, so now what have we got? We've got AK, the amplification factor, is 1 over 1 minus lambda k. We've got tau effective for the case mode is tau over 1 minus lambda k. And so what does the response look like? So obviously if lambda k is greater than 1, that's bad, and then we have divergence. So we don't want that. Now, what happens if lambda is positive but smaller than 1? So let's see. Let's draw a picture. Let's say if lambda k equals, if lambda is 0, then we just have an exponential. Here ak is equal to 1, and so we reach ck 0. And we have this kind of decay, the time to reach up to e over a factor of e of the final value, this effective time, is just tau. Okay, that's for lambda equals 0. The axes here, so this is time, and this is the value of ck at time t. Okay, so that's for lambda equals 0. What happens if lambda is larger than 0 but smaller than 1? Right, so we said over here, the amplification factor, if lambda is positive but smaller than 1, ak will be larger than 1. So we've got an amplification. That's good. But what happens to the time constant? The same thing, right? We have the same scaling of the time constant as the amplification factor. So if we make a larger, we're also making the effective tau larger. So meaning it will take the system longer to reach its eventual steady state. So it will look something like kind of keeps rising. The effective time constant that it takes to reach the same fraction of its final value will be larger. That's for t lambda between 0 and 1. So on the one hand, we succeeded in getting amplification, but it'll take the system a longer time to respond. And if we had an input that changed in time, so if you recall the form of the full solution, the time changing, I might as well write it. If this input was time changing, changing in time, so we would have something that looks like one over tau, and then maybe we should check this. we would integrate over the past up till time t, with the past value of the input, and it would be filtered by this exponential t over tau k. Sorry, t minus tau prime. So the past values are being offset by a decaying exponential. And then we would also have a factor, we'd have the same amplification factor. Should be on I have to check this in the break because I think this amplification factor might come out of the integral. I'll check it in the break. But what I wanted to point out was the exponential filtering. So in the same way that we slow down in the steady state, in the constant input case, we slow down the response. This filtering, if tau of k is longer, so it's filtering slower and slower, and we're kind of blurring the recent past together, and we're kind of not responding cleanly and quickly to the changes in the external input. So that's not what we want. So let's see. Back over here, what happens if lambda k is negative? So then what happens? Okay, if lambda k is negative, then tau of k can be very small, so we can get a quick response. But on the other hand, the amplification factor is also going to be smaller than 1. So we can get something that very quickly gets to its steady state value, but the steady state value is small. So this is for tau lambda is negative. So on the face of it, what we have is in a linear system, you have a trade-off between amplification and the time it takes to respond. So on the face of it, it seems that if our aim is to have a large and fast response, we can't do it with a linear system. Seems like we're stuck, we got to go on to nonlinear things. But after the break, we'll come back and I'll show you why, although this is a true analysis, it's misleading, and actually there is a way with a linear system to have both a fast and a large response. So we'll see that after the break. Any questions about this? Okay. And let's just pause. מזה אפשר להגיע לזה.
כאילו דילג.
זה יותר כללי.
מה זה אומר? זה לא כאילו...
זה נכון במקרה שזה...
שאלה לגבי השיעור שלנו. לא, היה את זה שפתחנו כאילו, שעשינו את זה, נכון? ואני חושבת שמטרה שלנו פה היא לדבר על מצב שאין פעולות כדי, כאילו, שהן משרפות. שהיינו שהמערכת יכולה להפעיל.
נכון.
ואז קראתי את ההלכה בסרט.
נכון, לגבי זה דבר קצת עדין, אנחנו כן חושבים על n שהוא גדול. בעצם n יכול להיות מאוד גדול, ועכשיו אנחנו אומרים בוא נגדיל את t. אז מבחינת הסטרלינג אז אפשר עדיין להגיד n מאוד גדול, אז יש לנו את הקירוב הזה. וכמו שאמרנו, רוצים לעשות את זה בדיוק, אז צריך לבדוק כמה טוב.
פשוט היה נראה לי שאנחנו נכנסים בתוך התהליך הזה, כאילו אחרי ששמנו בצד את הנושא של n.
אז עוד דרך לחשוב את זה שעדיין אנחנו חושבים על n שהוא מאוד מאוד גדול, אז עכשיו שואלים, אוקיי, אבל מה אני רוצה? עכשיו אני מחכה יותר ויותר זמן. כמה זמן אני יכול להניח את זה?
למה כאילו אמרת בהתחלה שאנחנו מתחילים פונקציה תאבית די, אבל אחרי זה התעלמת מכל התכונות שלה, אז למה לעשות את זה? כאילו למה לא להגיד שככה אנחנו חיים קבועות?
כן, כי פשוט זה יותר מתאים לתמונה בראש הפונקציונלית. אוקיי, אז אם אני עשיתי שינוי, איך אני אגיד אותו? זה הפתרון להיבט. כאילו שהיה פה מתמשך אחורה כל הזמן, אבל אני החזקתי אותו באפס עד כאן.
מאוד מאחלים.
יש לך אינפוט וקטור. יש לך אינפוט וקטור, ואתה אמרת באיזה כיוון הוא צריך להיות בשביל שאינטגרציה. אז זה מגדיר לך כיוון במרחב, ששם יש אינטגרציה.
מה עכשיו אדוני חוק משמעות? כבר נגמר המשפט, צריך משפט חדש.
אייגן וקטור. כיוון במרחב שעליו נראה את האינטגרציה לאינטגרציה.
זאת ועוד.
אז האורתוגונליות של האינפוט המקורי ב-R0 הוא לפרוג'קשן של R0 על הכיוון הזה.
מה זה הפרוג'קשן? לא הבנתי את הביגוד בין
אז אם יש לי פרויקט שזה...
הארץ המקורי, אני אמרתי, אני כאילו נותן לך.
כן,
זה אתה בוחר אותו. לא, אבל אתה בוחר את הכיוון. אז אתה בחר את הכיוון. כאילו אתה אומר מה יהיה הכיוון
לא של R0, של U0, של האינטגרציה, כאילו של הכיוון של
U0 אתה מצאת, ואז אתה אמרת, יש כיוון אחד שעליו אני רוצה עושים אינטגרציה. ואני עכשיו שואל, אוקיי, אבל מה יהיה אם יש לי R? חלק מ-R0 הוא לכיוון אורתוגונלי מזה.
בכיוון הזה.
הוא לכיוון אורתוגונלי מזה. יש לי חלק נגיד שהוא כן לכיוון הזה, שעליו אני יודע מה קורה באינטגרציה, אבל מה קורה בכיוון האחרים?
לא, מה שאני חשבתי זה שבלי קשר לכיוון הזה, אני נותן, יש לי R הוא וקטור, נכון R0, האינפוט, סבבה? אם פתאום ב-R של T, אז בצד הבא, כן, R של 0 של T פלוס 1, זה אורתוגונלי מזה, אבל זה לא הכוונה, נכון?
לא.
לא.
אפשר לחשוב על מה יהיה אם עכשיו, או נגיד עכשיו אני מוסיף. אוקיי, אפשר לחשוב, היה לי תקופת זמן שהיה לי כיוון, היה לי אינפוט בכיוון של אינטגרציה, עכשיו הפסקתי ויש לי כיוון עכשיו פתאום אינפוט בכיוון אורתוגונלי.
לא, אבל לעצמו.
אורתוגונלי לכיוון האינטגרציה. Okay, now this is actually on. Sorry, anybody who was listening the last hour. Okay, before we continue, just a note, I got confused with whether to put the factor here or not put the factor here, so just because I got confused, let me run it through for you guys. So what I just remember for myself as a fact is if I have tau x dot equals minus x plus f of t. Again, it's just assuming that we're starting at 0, at time 0, then I just remember this, after having worked through the integration factor some number of times, I just remember that this gives me a solution 1 over tau, integral of 0 to t, e to the minus t prime over tau, f of t prime, dt prime. I'm integrating over the past, exponentially discounting the past by this time constant tau, and there's a 1 over tau up front. So now, if I have the equation that we have, tau c dot equals, I'll just say minus lambda. We had a 1 minus, but minus lambda c plus f of t. So now the one thing I want to get to this form every time, so divide by lambda, write tau over lambda, and write f over lambda, and then plug it in to here, c over t. So in principle, I have lambda over tau, the integral, e minus t prime over, and here I have tau over lambda, this effective tau. And now here I have, instead of f of t, I have f of t over lambda. So the lambdas, in fact, cancel, and this should be prime and dt prime. Okay, so that's just, first of all, to show you that, we all forget these things, and at least the way I remember is that this kind of canonical form is when x doesn't have any coefficient in front of it. So I'll get to that form first, and then from there I know the solution. Okay, so here we saw what seemed like a very general conclusion, because we took a general linear network, said any linear network, as long as we have n eigenvalues, we can decompose it, we can solve it, and then we can see this kind of trade-off between amplification and speed. Which in other contexts is also related to what can be called gain versus bandwidth. I have a limited bandwidth because I have a limited speed of response, and gain is basically just another way of saying amplification. So there's a trade-off between those two. That's what it seems like in the general case. But now I'm going to introduce a specific model that shows that is not necessarily the case. And that model we'll call it balanced amplification. And the model is of two neurons. One is excitatory, and one is inhibitory, RE and RI. And it's very close to models we've seen before. We have excitation from the excitatory neuron, and we'll just, for simplicity, have the same strength excitation. And then we have inhibition from the inhibitory neuron, so minus JI onto both. These parameters are both positive. And then we have external drive into those. So we have, I'll just take tau, the basic time scale of the intrinsic time scale of the neuron, to be 1. Tau equals 1. So we have the equation for the excitatory neuron plus JERE minus ji ri, again a linear network, plus some external drive, h0e, and similarly for I, minus ri, the decay term, JERE minus JI RI plus HI0. Okay, so that's our network. We have excitation, inhibition. We're going to require also strong inhibition. At least for now, we'll require JI is larger than JE. Again, like I said, both of these are positive. Okay, so linear system, we'll do the usual thing. Greek chorus, eigenvalues. So let's see what we have here. We have the matrix J is equal to JE minus JI, JE minus JI. All right, what are the eigenvectors? What are the eigenvalues? Somebody should be able to throw me one eigenvector, and somebody should be able to throw me one eigenvalue immediately. 1, 1. 1, 1. That's always the best one to guess, especially we have something that has this symmetry, it repeats. 1, 1 is an eigenvector. Okay? That's clear. We have P1. I'll call it P 1, 1, and that has eigenvalue, which is equal to what? JE minus J1, minus JI, JE minus JI, which is negative. Just to be paying attention. Okay, now somebody should be able to throw me another eigenvalue without blinking. That's already a little more complicated. Just the eigen, I was just being a little like more humble. Just the eigenvalue. Just. Oh, the other one. Wait, which one? Plus JI.
Yeah, and then the vector is 1 minus 1.
No, that's not going to be an eigenvector. Why is that not going to be an eigenvector? Or come back to my question. What's the other eigenvalue? Immediately, that should be like the first thing that jumps at your head when you see this matrix. Even before, 1, 1 eigenvectors also, but even before that, I think, what's the eigenvalue of this matrix? What's the rank of this matrix? This is a rank 1 matrix, right? It has identical rows. It's a rank 1 matrix, so there must be a 0 eigenvalue. So, without even thinking about it, immediately. Lambda 2 equals 0. Okay? And then it tells us the second eigenvector, P2, that gives us 0 should be JI on the first element, and then JE on the second element. Right? Is that clear? Okay. So that's great. We can write, as we've done so many times, in the basis of these eigenvectors, C1 should be equal to minus 1 minus lambda 1, which is plus JI minus JE. C1 plus whatever the external drive vector is going to be, whatever that's going to turn out to be projected on the first eigenvector, the uniform one. And then C2 dot is just going to be equal to minus C2, right? Eigenvalue there is 0, plus whatever the external drive is there. And now, it looks like, if we go back to our picture that we had before, which was very general, we have this amplification factor, we have this tau factor, we have one eigenvalue that's 0. So C2 is going to have kind of the unaffected tau, the intrinsic tau. So that's whatever speed it is. and then it's going to have also, it's just going to give the response of whatever the input is projected on that mode. That's going to be the response 1 to 1. And then for lambda 1, the first mode, well, we're going to have lambda 1 is negative, so we have a faster rise, so we have a quick response, but it's going to be smaller. So it seems like this is not anything too useful. And let me hold on here. I want to draw another picture. So here, lambda 1 equals lambda e minus lambda I. Lambda 2 equals 0. Okay, so we have our second picture. C1 has this lambda 1 equals je minus ji less than 0. C2 doesn't have any self-coupling. It's just got its own intrinsic decay. So on the face of it, it looks like that just gives us a shrinking. We don't have any amplification, maybe a faster response. That's what it would look like. But that's not the case. So let me show you now why that's not the case. The key is, so everything that I said is true about like the amplification and the time factor, but it's true for these components of the Eigen basis. Right? So we're looking at dynamics of the Eigen basis. We don't know exactly what the dynamics will look like if we return, for example, to our standard basis, or if we look at a different basis. So we have another basis turns out to be very useful, and it's worth pointing out that it's a unitary basis. So we have what we'll define as U1 is just going to be 1, 1, which is the same as P1. I guess, okay, I'll come back to that. And U2 is going to be 1 minus 1. Okay, so these are two orthogonal vectors. I'll note that they're not normalized here. So the matrix U is currently not normal, and I'm kind of deliberating with myself if I should normalize it now, even though I didn't do it in my notes. I will. Hope it doesn't get me into trouble later. But now I have normalized vectors that are orthogonal to each other. I can see my matrix U 1 over square root of 2, 1, 1, 1 minus 1 is unitary or orthogonal. I have that U inverse equals U transpose. You guys can check that, but it should be obvious by the orthogonality relationship and the fact that each of these are normal. We know that holds. Okay, so now let's take our connectivity matrix, and we want to see what that matrix looks like in the basis U. So J relative to the basis U. Okay. So how do we do that? That's a good thing to also know how to do. There's like formulas you can kind of write to give you that. But the way I always think about it is I just calculate the matrix times one of the vectors. And then what I want to do is write this product as the sum of the two basis vectors and just see what the coefficients are. Right? So, okay, let's see what J times U1 is. Well, U1 is the same as T1, so it's an eigenvector. And we have the same lambda 1. So we know that it's gonna give us. I'm gonna write it now this way. minus ji minus je, or je minus ji, as we saw before, times u1. I want to change I'm going to call this u1 as u plus, because this is like the sum mode, 1, 1, and u minus is the minus mode. U2 is U2 is the minus mode, so I'm just going to give them different names. U plus. So we see that u plus, we know u plus is an eigenvector because it's identical to p1, so we just get this. Now what's j times u minus? All right, well, let's just write it out. Je minus ji, je minus ji. 1 minus 1 here. So what do we get? We get je plus ji, je plus ji, and we have still the same 1 over square root of 2 factor. So essentially we can pull out the je plus ji, and again we have the sum mode, so we have u plus, right? J times u minus is equal to je plus ji times u plus. So I'm going to write this now as the effective connectivity matrix within this basis. So for the sake of that, I'm going to call this term here ji minus je. I'm going to call that j plus, because that's what connects the plus mode to itself. And now we have j times u minus is equal to je plus ji. I'm going to call that jff for j feed forward, which I'll get into exactly why I'm giving it that name. And now, so what's the connectivity matrix in that basis? So the first column is where we sent the first basis vector 2, which was just to itself with this factor j plus, minus. I have a minus out front. The reason I did that was because I want my j's to be positive. All the j's in the whole thing are always going to be positive, and if we have an inhibition, it'll show up with a minus sign, so we have minus j plus, right? This is a positive value, and then 0, because it doesn't send, the matrix doesn't send u plus to u minus at all. And now u minus is sent only to u plus with this factor of j feed forward and a 0 down here. Okay, so this is our effective connectivity matrix, and we note that it's upper triangular, which just to already draw a connection to Jonathan's topic of the feed forward chain, working memory feed forward chain. There we saw, well, actually it was a lower triangular. I probably should have set this up so that it'll be lower triangular, but it doesn't matter too much. So we notice that, and now we can write the dynamics in this basis. So we project the original dynamics onto this basis. The way we do that, if we have RE, RI, we're going to want some R plus coefficient, which will be a function of time, times the vector U plus R minus U minus. And we know that we can write the dynamic equations just directly using the matrix within that basis. So we have R dot plus equal to minus, and here we have 1 minus J plus R plus, it's going to have J feed forward, JFF, times R minus. Meanwhile, R minus dot is just going to have minus R minus, just the decay term. Okay? Is it clear how we get... I forgot, of course, there's some external input projected on here, which we'll give some kind of name, H plus 0, whatever, h minus 0 in general. Is it clear how we get that? So this is just a different basis. And now we can see what happens to R minus. It's kind of unconnected. It has whatever input it has, it just decays. It's kind of the tau equals 1 situation. But now R plus has its own dynamics, which are governed by 1 minus J plus, which is a positive, okay. This is actually plus. The effective connectivity is minus J plus, and so the effective scalar here, like if we think of what we had before was 1 minus lambda, it's like with a negative lambda, right? So we have 1 plus J plus. So the effective time scale of R, just kind of seen as its own mode, is actually faster than the intrinsic time scale. But additionally, it's got this effectively feed-forward input that's coming from R minus. Right? So if I just write this set of equations, or think about the system in this basis, I go back to my schematics, and I'm going to add a third schematic here. Now I have these modes R plus and R minus. Now we're used to changing bases and going into the Eigen basis where things are separate. In here, things are not separate, but what we have is a situation where R minus doesn't get any input from R plus. So we have R minus sending to R plus by JFF. And what sign is JFF? It's positive. And we have R plus just sending back to itself an inhibition, minus J plus. And that's our system in this third basis. So in this third basis, we can see that there's an effective feed-forward structure that's hidden in the original connectivity. We saw this original connectivity, it's all recurrent. We saw the eigenbasis in there, obviously things are separate by design. But here we have a basis where there's feed-forward input coming into R minus. So we can think about what can happen. We can have, for example, strong input only into R minus. However strong that input is, R minus responds just with the time scale of a typical intrinsic time scale. And then it can pass that along as a feed-forward input to the next mode, R plus. And JFF, well, that could be really large. Right? So we can have these two neurons with their excitation and inhibition really fairly strong excitation, and we just require that JI is larger than JE. But both of those terms can both be really large. For example, in such a way that we could keep J plus still kind of small, order 1, and make JE and JI, each of them very large. And then we can be passing a very strong weight feed forward effectively to this mode R plus. And you'll have maybe a homework assignment to simulate that and kind of see it by eye, but I just want to draw schematically what the results of that look like, both within the basis R plus and R minus, and also back in the original basis. R minus. So what does it represent? So when we have orthogonal basis vectors, it's fairly easy to understand what they represent. Because to recover, if we want to know what R minus is from the original vector R, RE and RI, we just take U minus dot R, right? So what is U minus dot R? Well, that's proportional to just RE minus RI. We have this scaling factor because we want it to be normalized, but the point is this is representing the difference between excitatory and inhibitory neurons, right? And similarly, R plus is proportional to RE plus Ri. It's representing their sum. So sum in different modes. So essentially what we have is that the difference mode is disconnected from anything else. If there's a difference between the two, that difference decays. But before it decays, that difference projects as it was to the sum. So if we start with a situation where we made the two neurons different, so they're going to come back and align to each other, but meanwhile their sum is going to increase. So I have no idea what that is. Oh, that's what I was listening to before I came. Okay, so one example. Mm-hmm.
Why would we want to make it more complicated? I thought we were aiming to reduce the dependency
Right.
between the eigenvectors.
Right.
Why would we?
That's a really good question. We know that the eigenvector is a very useful basis because it makes everything simple, it eliminates the dependency between them, and then we can solve directly. So in terms of the algebra, that's the most useful thing. What I want to suggest is that in terms of the intuition of what's going on in the dynamics of the system as a whole, in this case, this is actually a more useful basis to understand intuitively. And I'll basically say why now. In the eigenbasis, so I'll take an example, which is of taking the external drive, say to E, to be just a delta function at time 0, without input onto the inhibitory neuron. So essentially, if I take a delta function input to the excitatory neuron, that's equivalent to just setting Re at time 0 equal to 1. So I'll just take that as an initial condition, just as an example of what happens in these dynamics, and leave Ri at time 0 equal to 0, and then plot what happens. So we have Re starts at value 1, and Ri starts, more colors here. Let's do red and blue for I and E. The red are Re and Ri. Now, okay, so the point is this: what might we think? Intuitively, if we did like what we were taught to do and decompose it by the eigenbasis, and then look in the eigenbasis, which we did over here, we saw that kind of both of the eigenvalues are negative. There's one that's negative, there's one that's 0. It seems like everything's just decaying. In the eigenbasis, everything is decaying. So we would think, okay, presumably then just like Re decays and maybe Ri kind of stays where it is or something like that. But it turns out that both of them actually increase at first and then decay. This is Ri. This is Re. And naively, just from looking at the eigenbasis, we don't have any intuition about how that could be, because in terms of the eigenbasis, everything's just decaying. What this basis tells us is that something else is going on. I've increased Ri. There's a difference. The difference mode all of a sudden has a difference of 1 in it, and that is driving the sum mode. So both the difference and the sum. Green here. Both the difference and the sum start. I guess if we're going to be fully formal about it, they both start at 1 over square root of 2 with this normalization. And now we know that the difference mode doesn't have any feedback, so it's just got a decay with a typical neuron time scale. That's R minus. But it's driving, with a strength JFF, the sum mode. So the sum mode, and I forget. The sum mode is going to look something like this. R plus. So if I think about this set of equations, I can first solve this one because it's independent. So it's true that this basis is a little more complicated than the eigenbasis. They're not fully independent, but I can solve it iteratively. I can solve it one step at a time. Because there's no feedback to R minus, I can solve R minus alone and just get R minus is just a decay. R minus of t is R minus at time 0, E minus t. For this example where my input was just a delta function. And now R plus of t, I have my general form I have the general form where it's integrating over the past, and now it's integrating over the past of the value of R minus. So it has 1 plus j plus in here. It has this integral over the past times with an exponential filtering, t minus t prime. Again, the effective time scale of plus, the effective time scale tau plus is 1 over 1 plus j plus. So let me write my solution like that. 1 over 1 plus tau plus, and then I have this exponential filtering with filter constant tau plus, and then I'm integrating over the past value of the minus mode, the difference mode, past time t prime dt prime, and then I have this factor. Very importantly, have j feed forward, which, like I said before, can be strong. So these are my two solutions. It's true I don't exactly know what this looks like, but I know what R minus looks like. It's just a decay, and I know that at time 0 and immediately afterwards, R plus is receiving this positive input, and it's going to be a little bit lagging R minus, but not by a lot. That's a crucial thing. The effective time constant on this plus mode, tau plus, is just 1 over 1 plus j plus, so it's a little bit smaller than a typical time constant. It's faster, and like I said, we can tune the system so that that's not a very big number. It's order 1, while JFF can be large, and so that's going to essentially be driving positive input. So long as R minus is not 0, there's some positive input coming into R plus, until eventually that input fades away, and then R plus just also decays. Right, and then it turns out that that's enough such that back in the standard basis of RE and RI, both are gonna go up at first. So there's this transient rise, a transient amplification in the dynamics. And we wouldn't have known that just by looking at what happens within the eigenbasis. Okay. To try to clarify that a little bit more, I'll go to a geometric picture in a second. Are there any questions up until here, though? Okay, so now let me draw a geometric picture here. RE, how did I do it? Yeah. In the y-axis, I'm drawing RE. In the x-axis, I'm drawing RI. So that my initial condition is here. And now I have the vectors. Let me draw the vectors involved. One vector is U plus, which is just along the 1, 1 direction. So that's u plus vector. And like we said before, that's one of the eigenvectors also. That's P1, which had a negative eigenvalue, lambda 1. Is that right? What was negative? Yeah. Okay. So we have P1 and u plus, that vector. We have the orthogonal u minus. And the last vector of interest will be our second eigenvector, right? Which was not orthogonal to the first one. So the second eigenvector, JI, and we said JI is going to be always larger than JE. So that has some upward slope like this. That's P2. Okay. So let's try to see what's going on here. Let's now go back to the eigenbasis perspective. We know in the eigenbasis perspective, at some level at least, things are very simple because the dynamics are independent of one another. But what's the first thing we need to do if we want to go to the eigenbasis? So we have to project the initial condition onto the eigenbasis. And this relates to something I said at the bonus hour last week, I think, which is that the naive thing, I look at, okay, what's my projection onto P2? The naive thing we think about is an orthogonal projection. We just say, like, okay, this initial condition projects here onto the vector P2. But that's not the case. In a basis that's not orthogonal, you can't just take the orthogonal projection. So how do you figure out where the real projection is? One way to do it is to invert the matrix. But geometrically, what I do is run one of the vectors through this point. Arbitrarily take P1 and just run a parallel line through that point and see where it crosses P2. Oops. So that gives me the projection along P2. And so my starting position is made up of, I've moved this much along P2, but now I have to move this much the other direction along P1. And so totally counterintuitively, the initial condition along P1 is way down here. Right? If I add up these two vectors, I get here. And that's where the source of confusion is, because it's true now, if I look within the eigenbasis, what's going to happen is both of these are just going to decay, as we saw. Both eigenvalues are, one's negative, one's 0. We just have the decay, right? But it turns out this decay is faster than this decay because we have lambda 1 is negative, while lambda 2 is just 0. So this decay is actually pushing the dynamics in this direction. So the initial dynamics are along the first eigenvector, which has a more negative eigenvalue. The initial direction is going to be parallel to that. And then eventually, the decay is going to be dominated by the second eigenvector, which is the slower one to decay. So we can use the eigenbasis to figure out what's going on. Of course, the eigenbasis gives us a full solution, but we have to keep in mind the complicated result and counterintuitive result that we get because the two eigenvectors have a significant overlap. So because of that overlap, we have a totally counterintuitive picture, even though it's true that both components of the eigenvectors simply decay. The net result of the dynamics has this transient amplification. So we actually have a rise in the resulting dynamics. And we could see it from the orthogonal basis, which I didn't draw all of that orthogonally, but in the orthogonal basis, that we have some starting, in the orthogonal basis we can do the intuitive thing and just take the orthogonal projection. This comes down to here, and that's the initial condition along u minus, and we know that that simply decays, but while that decays, it's giving a feed-forward push along the direction of u plus, and that's exactly what we see also in the dynamics. We get a push in the u plus direction, and then eventually a decay back along the second eigenvector. So that, again, that's the geometric picture of the same schematic, which we saw here. Everything's confusing in the recurrent picture. The eigenvalue picture, the eigenvector picture is clear because the dynamics are independent, but there's a complicated overlap between the eigenvectors. So the projection is not intuitive when we go back to the real basis, whereas this basis is orthogonal, and so it gives us an intuitive picture. It's just a rotation of the plane, and it shows us that there's a feed-forward, effective feed-forward push from one mode to the next. Okay? And another way to point out kind of what's going on here is that let's say that we look at the net activity in terms of just the norm of the vector of where this is at any given time. So r of t, take the norm squared of that. So we can also think about it as like a total variance kind of the activity, or total power of the activity. And if we could use that as just to kind of give us a sense, what's the total power in the activity? How much activity is there? One possible measure of that. Okay, so if we look in the eigenbasis, how do we go to the eigenbasis? We have R. So how do we get to the eigenbasis algebraically? We take our basis, our eigenvectors, combine them into a matrix P, and we know that when we go to that, in the eigenbasis, we have P times C vector is equal to our original activity, right? Because that's how we decompose the activity as a sum of the two eigenvectors. Okay.